All right, so we're just going to keep continuing with hypothesis testing. We'll work through some more examples today. Tentatively, and I'll get an announcement posted and mentioned in class Wednesday, but tentatively the exam is going to be next Monday and Tuesday. So kind of like the last one, it's going to be on Canvas and open over like a 48-hour time period. Like I said, we'll kind of see where we get through today. I think we'll be in a pretty good place finishing up hypothesis testing. I may also post a couple of additional videos this week, which is I posted a folder with a bunch, 2 practice exams. So I may be posting a couple extra videos of just me working through some of those practice exam problems, because although I think we'll be able to do some of them in class, maybe some of the easier ones, like going back to maybe like the uniform distribution, instead of taking the time in class to do those, I may just post additional videos of me kind of working through those, okay? So if you see those, that's why, right? You kind of have that Excel assignment that's due at the end of the week. What I might also do is create a Connect assignment, but it's not an actual assignment. It's just going to be problems that you can work on for practice, kind of on hypothesis testing. So if I put that up there, it may look like it is worth 1 point. I can't set it to be 0. That's just the way the Connect assignments work for some reason. Although after talking with them actually 2 weeks ago, I think they're changing that. So I may get a practice kind of homework up there, but it's really not a homework. It's just problems that you would have seen in a homework that you can kind of work on to practice for the exam. Or just practice hypothesis testing. So where we left off last Friday was we started to figure out what these p-values are, right? So the idea was that we saw some sample mean. We could turn it into what we were calling a test or a z-statistic. Using that test or z-statistic, we could find, okay, what's the area to the left of it for a left-tailed test, area to the right for a right-tailed, and then for a two-tailed, depending on which one we saw, kind of the area in the tail, and then multiply it by 2. So once we had that p-value, we said we can reject the null if that p-value is less than whatever alpha we've set. We'll talk a little bit more about alpha today and kind of what it represents to us, but last class, what we kind of, what I explained it to you as is you're kind of setting this threshold. If anything is less likely than, say, an alpha of 0.05, or the probability of seeing it is less than 0.05, then we're okay rejecting it. And if it's not, well, then we're not okay, right? And we would fail to reject. So that was kind of our rejection decision. Boiled down, it was the p-value less than this alpha threshold we set. Okay. This was kind of the more formal kind of definition of the p-value. We'll work through some problems, and I think this will become a little bit easier to kind of think about why it's written this way mathematically. Okay? So this was all things we looked at, which led us to kind of, our final kind of steps we could put together. And then I'll show you, we're going to work through a problem here with some actual numbers in a second, which was the example that we had really kind of used on Friday. First of all, figure out what your null and alternative are, right? It matters what type of tailed test you have, left, right, or two-tailed. Figure out what that threshold is that you want to set for alpha. Calculate your test statistic. Using the test statistic, find the p-value. And then if the p-value is less than alpha, you reject. If it's not, you fail to reject. Those are kind of our steps for every single hypothesis testing problem we'll work through. So we had this example where we said we wanted to test for whether or not it's, less than 7%, right? We had that sample of 36 beers with a sample mean of 4.5. Let's assume, right, this is one of those that we're going to have to either be, it's going to have to be given to us, but assume what we're told that the population variance is 1%, so 1 here. Can we reject the null hypothesis at the 5% level? So I'm going to kind of show you how we could work through one of these. I'll wait for this to catch up, and then we should get going here. Okay, so we said we wanted to test for whether or not that true mean was less than 7%. So what we want to test for, what we're trying to find, is our alternative hypothesis. Okay? So is it less than 7%? So what are we going to do? Well, the null is that we'll assume the opposite is true, kind of stacking the deck against ourselves. Just like we said, in a court case, you stack the deck against yourself and assume someone's innocent. Okay? So we've got a less than sign in the alternative hypothesis, so we're dealing with a less than or a left-tailed test. Okay? The sample mean we found was, just as a reminder, 4.5. Sample size was 36. And I believe the alpha was 0.05. That top one's the null. Yep. So this is what we're trying to determine whether or not we reject or kind of fail to reject it. Now, we found evidence that goes against the null. So we know that potentially we can reject, but does it go against it enough? Well, if we use that assumed true value of 7%, we know that if that was the true value, the sample mean should be normally distributed around that, okay? So our assumed true mean of 7% is what our sample means should be normally distributed around if, in fact, that assumption is true. Here we can calculate kind of an intermediate step, and I'll show you two ways of doing it. So what would the standard deviation of this sample mean be? Well, we have the equation. We know that's simply the original population variance over my sample size. So what? The square root of 1 over 36. Kind of made it easy here, making the variance 1. We found this sample mean of 4.5, and the p-value would then, for the left-tailed test, be the area to the left of that, right? Or the probability that we saw a sample as far away from that assumed true mean as we did, or anything even further, anything more extreme, right? So we can kind of think about, here's our p-value. But this is just a normal distribution, so we can't really find that. What we need to do is turn this into a z-value or a z-statistic so that we could look that z-value up on the table, and the table would then tell us the area to the left, which was our p-value. So what's the equation we had for that z-statistic? Excuse me. So we'll take that sample mean value we found, subtract the assumed true mean, and here's where you could do it one of two ways. Well, I've already have the intermediate value you calculated. I could just plug that into my denominator. Right? Here I calculate that intermediate step. So I don't know, this is what? 4.5 minus 7 divided by the square root of 1 over 36. Okay. Now, we found a sample mean below the assumed true mean. So automatically we know that this test statistic should be, remember, a z-statistic is still representing a z-value, a value coming from the standard normal distribution. So our z-statistic will represent the number of standard deviations below that assumed true mean that 4.5 is, or the number of standard deviations below the assumed true mean our sample mean was. Any questions up to this point? So this is kind of where we left off last week, but kind of working through everything like all in a row. I was kind of showing you different bits and pieces last class. Okay. So if we actually plug those values into our calculator, we get about -15. So right away, we should be thinking this is pretty large as a test statistic. Because remember, when we were looking at z-values, if we look at the table, help if I had them pulled up. So we look at this z table. The lowest it goes is -3.99, I guess. But the area to the left of that is pretty much 0. So if I'm looking at a z-value or a z-statistic of -15, the area to the left of that is going to be even closer to 0, right? I'm just looking at a z-value that's even further into that tail. So I get a p-value here of pretty much 0, right? Because if my test statistic was -3.9, the area to the left of that is 0. Well, if it's -15, it's an even smaller area, right? So this is kind of an easy one in that my p-value is essentially 0. Well, if I make the rejection decision based off of is my p-value less than alpha, right? Well, yeah, 0 is clearly less than 0.05, so I reject the null at the 5% significance level. Or said differently, I can reject it with 95% confidence. Okay? Kind of works just like the confidence intervals. Alpha is essentially telling us, like, we'll get into a little bit more in a second here, but the probability that I'm wrong, right? And so the probability I'm right would just be, whoever gets me up to 100%. So if the probability I'm wrong is 5%, I can reject it at the 5% significance level. Well, I'm rejecting it with 95% confidence. And I could test against different alphas. I could just start choosing, right? Maybe I want to test against 0.01. Is my p-value of 0 less than 0.01? Sure is. So I can also reject at the 1% significance level, or I can reject with 99% confidence. Any questions on this before we kind of jump into another example? Hopefully you guys can hear me okay on Zoom. If the audio does anything weird, make sure you let me know. All right, and then this, I don't know, I thought this meme was funny at one time, but now I like craft beer, so here we are. So let's say we had a different example, right? Just some different values, kind of different setup. And we go back to that one where I said, okay, maybe a sociologist wants to determine if the mean retirement age is, actually here I have greater than 67. Okay? So we want to know, is the mean retirement age greater than 67? Right? That's kind of the setup. Okay? So if that's the scenario, right, we take a sample of 25 individuals and we find a mean retirement age of 71. So we know that, you know, retirement ages are normally distributed with a population variance of 81. Okay? So somehow we know the population variance. Don't ask how, we just somehow know it, right? We'll get into more practical applications where we don't know the population variance probably on Wednesday. So what is the p-value for this hypothesis test? Well, let's think about what we're doing here. And I'll kind of make this larger here in a second, but so we have the words to go off of. I think my markers are dying. So we want to know whether or not the mean retirement age is greater than 67. So what do we want to test for? Well, we want to see, is that mean retirement age greater than 67? Which means the null hypothesis would be the opposite of that. What we assume to be true, stack the deck against ourselves, is that's less than or equal to 67. So based off the alternative hypothesis, what type of tailed test do we have here? We look at the sign in the alternative hypothesis, we have a greater than sign, right? So greater than or right-tailed test. Okay? Only values that are above 67 are going to go against the null. So only values on the right side of the distribution would be ones in which we potentially could reject the null. Okay? So we've identified our null alternative hypothesis. Oh, was it 71? No, I probably should have left that up now. Yep, mean retirement age of 71. There we go. We had a sample size of 25. And I believe the population variance was told to us to be 81. Okay? So I haven't specified an alpha yet for a reason. Okay, so I'll show you, we could test against several different alpha values, but only really having to do this problem one time. So we'll find the p-value first, and then we'll think about, okay, what, if I compared it to these different alpha levels, what would the outcome of this test be? So if what we've assumed to be true is in fact true, we only need to test this kind of cutoff point for the range of our null hypothesis. So we can use the assumed true mean of 67. If we can reject 67 as the true mean value based off our sample, we could reject any value below it as well. Okay? So we found a sample mean of 71. Remember, this is the distribution of our sample means. I could calculate that intermediate value, which is the standard deviation of my sample means, which is just the square root of 81 over 25. Okay. I think this ends up being, what, 9/5, so just under 2. From there, what I need to do is turn that sample mean that I found into a z-statistic, right? How many standard deviations away is 71 from that assumed true mean of 67? Now I have a right-tailed test, so the probability that I see something that goes against the null as much as I did from my sample, or anything that would go against it even more, that's going to be anything that's further away from that assumed true mean of 67. So now this right tail would represent my p-value, right? Once I turn it into a z, right, I can look this up in the table and find that area to the right. Okay. So how do I calculate that z statistic? Well, that's just my sample mean minus the assumed true mean. And then here, I could write it all as one formula, or I could remember that this denominator represented that intermediate value that I found, which was the standard deviation of my sample means. Either way, I've got what? 71 minus 67 divided by the square root of 81 over 25. So if we enter that into our calculator, let's see what we'd end up getting. Oh, so approximately 2.22. Okay. So we round it to the second decimal, we get 2.22. So there we go. I go down here to my standard normal table, I scroll down, 2.22, so the second decimal is 2, so I go here, 2.22. The area to the left is 0.9868. Okay? So the area to the left here, 0.9868. Well, remember, my p-value was the area to the right of my test statistic. Hold on, we're having some, okay, well, okay. I don't know why I did that. So when we looked that area up in the tail, right, we looked up our z statistic of what, 2.22. We found that area to the left was 0.9868. Did you guys see me go through that on the table? How did it cut out after that? Before the table? Okay, so all we did was go to this table. The second decimal we had was 2, 2.22. The area to the left is 0.9868. So we're still using the table like we did before when we had z values. However, the table gave me the area to the left. That's not my p-value, right? I had a right-tail test. I wanted the area to the right. So I still have to subtract it from 1. Okay? Any questions over anything there? So what, 0.0132? So now we can start to think, okay, I've got my p-value. I can actually do several different hypothesis tests really quickly. And this is kind of the one advantage of hypothesis testing compared to like confidence intervals. I mean, you can think about with confidence intervals, I could say, well, this value is not my confidence interval, so I can kind of reject it, right? Well, here, once we find that p-value, I can, it's a lot easier to test really against any alpha I want, right? So I've got that p-value. Of 0.0132. Okay. I can do tests pretty easily, right? So is 0.0132, is that less than alpha of well, actually here, let's go 0.1 first. Well, sure enough it is, so I can reject at the 10% significance level, or I can reject with 90% confidence. Is 0.0132 less than 0.05? Sure is, so I can reject at the 5% significance level, or with 95% confidence. Is 0.0132 less than 0.01? Well, it's not, so I actually fail to reject at the 1% significance level, or I fail to reject with 99% confidence. Okay? So I can reject at the 90 and 95% confidence level, but not at the 99 here. Okay? The evidence I found here went against that assumed true mean of 67 quite a bit. In fact, it was the likelihood of seeing 71 as that mean retirement age. If the true retirement age was 67, the probability was only just over 1%. Right? Well, if I was okay rejecting anything that was less than 10 or 5% likely, then I would have rejected. But when I set that threshold to 0.01, or I only wanted to reject if the probability that I saw the sample mean I did was less than 0.01 or less than a 1% chance of occurring, well, I didn't quite meet that threshold, right? Didn't quite meet that standard. It's really close, but I didn't quite make it. Okay? Any questions on this idea of rejecting? And once we found that p-value, it's just easy to quickly do this against all these different alpha values. Okay. So another way of thinking about this p-value is if this is our rejection decision, when the p-value is less than alpha, once I find that p-value, essentially it's telling me the last threshold for which I could reject, right? Any threshold I set above 0.0132, I'm going to be rejecting it. Any threshold or alpha set below this, well, now I'm going to fail to reject. This is essentially the last probability that I could reject that, right? Yeah. Zero, so 0.0132? Here? Oh, so you can think about it here. We really could answer several questions, right? The setup or the process for which you would find the p-value is the exact same, right? I'm doing a hypothesis test. Alpha is just essentially, okay, ahead of time, before I would have done all this work, I'm going to set a threshold that I'm comfortable with. If I see a sample mean where the likelihood of it occurring is anything less than a probability of 0.1, then I'm going to reject my assumption, right? If I set that threshold at 0.05, I'm only okay, rejecting the assumed true mean that I had. If the probability of seeing my sample mean was less than 0.05, right, then I'll set that. So these are almost like three different problems, right? I could ask you, do you reject at the 90% level? Do you reject at the 95% level? Do you reject at the 99% level? And here, we reject based off the p-value. The p-value is always going to be the same, right? We're just testing it, kind of like confidence intervals. I'm building my confidence interval around the same sample mean every time. It's just that here, not finding upper and lower bounds, I'm actually finding this p-value, which is the probability I saw the sample mean I did if the assumed true mean that I had was in fact the true mean. Okay? Does that answer or make it a little more clear? Okay, any other questions before we keep moving here? Okay, so where are we at in time? All right. I think we'll have time, so let's go to the next one. So that was our p-value. I've got kind of a summary slide eventually. It's just that I made one slide for both these examples we're going to go over, but I kind of jumped the gun, and we kind of saw that, I could reject here. I set different alphas here. I even set alphas at 0.2, but the idea is still the same. We're just checking to see if if the p-value is less than alpha, we can reject, and when it's not, I fail to reject. Okay. So let's go through another example. So I went out and looked at this. I think this was before last fall. So there's this group that says that back to school spending is on average $606.40. Okay. I expect, or a researcher expects that the average back to school spending differs. Why does it keep doing this? I only have to switch it one time. We're getting kind of the blue screen of death. All right, there we go. So they claim that the average back to school spending is $606.40. A researcher thinks that it differs from this amount. So remember, anytime you see this word like different or differs or different than, we should be thinking about a two-tailed test, right? We don't care if we see a sample mean above this value or below it. We just want to know, does the true back to school spending differ from this reported amount of $606? Okay. So what we've got here is that true mean different than or not equal to that reported amount of $606.40? So what am I going to do? Well, I'm going to stack the deck against myself and actually assume it is equal to that amount. Okay? So I've got a two-tailed test here, so things are going to be a little bit different. We're going to have a little bit of a hiccup once we get to the p-value, right? Because now both sides matter. So I take a sample of 30 families, sample mean. Just write this down so I don't forget it once I switch to just the .chem. So we've got our sample mean of $622, sample size of 30. We somehow know the population variance, maybe based off some historical data. What are the null and alternative hypotheses here? Well, we've already kind of identified everything we were given from this problem. And in that process, we identified B as our null and alternative hypothesis. Okay? When you're thinking about constructing the null and alternative hypothesis, your sample mean value should not be the value in your null and alternative hypothesis, right? That's your evidence that you're trying to either reject or fail to reject your null with. So the sample mean should not be the value we're using in our null and alternative hypothesis. It's more like a value that you're trying to test against that someone has reported or someone has, kind of published this out there, which was the $606. Okay. Any questions up at this point? Just the identification. So we've got a two-tailed test. Okay. The next question, okay, what's the p-value? All right. So we've got all the information we need. We're going to start working through this as, all right, well, the distribution of my sample means, if what I assume to be true is in fact true, should be distributed around that value, right, that population mean. Now, we could calculate the intermediate step here, which is that the standard deviation of my sample means is equal to the square root of my population variance over my sample size. We're kind of getting used to this. So the next step is, okay, what did I see as my sample mean? 622.85. So the probability that I saw that sample mean, if in fact what I assumed to be true was true, would be the area to the right. But remember, the p-value is the probability that I saw a sample mean as far away from that assumed true mean as I did, or anything more extreme that goes against that null hypothesis. Well, guess what? There's something on the other side that's just as far away from that assumed true mean, and that goes against the null hypothesis just as much, because now if I see 622 or I see, I don't even know, what is this going to be? So 26 below it, so about 580. It would have been equally as likely for me to see the sample mean of approximately 580, and any value past that would also go against my null hypothesis now, because now both sides matter. So I have this, I can turn this into a test statistic and find the area to the right of it, but this is no longer my p-value, it's only half my p-value. Okay? So, same kind of process though, I'm gonna turn that sample mean into a z-statistic. I can then use the table to find the area to the right, but I have to remember, I have a two-tailed test, I have the same tail on the other side, so once I find this, I need to multiply it by 2. Okay? So let's calculate that z-statistic. It's my sample mean minus the assumed true mean divided by, and we could, if we had this calculated ahead of time, just plug that in right here, or we can do it all on one line, like this. So it's going to be what? 622.85 minus 606.40 divided by the square root of 4,225 over 30. Okay? So I don't know what this ends up being. So let's cheat here real quick. And first of all, if I'm looking at these possible answers, which of these don't make any sense at all? I'm looking for a p-value, and that represents a probability. A doesn't make any sense. I can also think about p-values as high as 0.9. I mean, I guess it's possible because I don't really, looking at the values, I can't quite determine what the standard deviation is. But, to have a p-value of 0.9, it basically would have to be almost no standard deviations away from that assumed true mean. So let's actually just work through it. We've got everything, we plug those in, we get 1.39 was our test statistic, right? So our test statistic, or our z-statistic here, was 1.39. We'll go to our, we're having technical difficulties again. Why does this keep switching to? See if this works. All right, I don't know what's going on. So we had that z statistic or test statistical equation, we get 1.39. So we go to our table, 1.3. Let's see if we can get this all in one line. 1.3, go all the way over 9. So 0.9, nope, this is the right row, 0.9177. Okay? So 0.9177, but 0.9177 is going to be the area to the left. That's what the table always tells us. We want the area to the right, so 1 minus 0.9177. But then remember, we then still have to multiply that by 2. Okay? So it's going to be about what, 0.16-ish? If we do that math real quick. About 0.16. Okay? Any questions over any of those steps? Okay. All right, so 0.1646. What we could then do is take that p-value and determine which of these alpha levels can we reject the null hypothesis at. Well, here we're being pretty generous and said, well, look, anything that's, less likely than what, 20% here, or a probability of 0.2 of occurring, we're going to reject. Sure enough, our p-value is less than 0.2, so we can reject with 80% confidence, right? At the 20% significance level, or 80% confidence. However, our p-value of 0.16 is not less than an alpha of 0.1, so we would fail to reject with 90% confidence. And then if I fail to reject with 90% confidence, well, then of course my p-value won't be less than, if it's not less than 0.1, it's not going to be less than 0.01. So I would fail to reject with 99% confidence as well. Okay. Any questions here? Once again, like each one of these alphas could almost be like a separate problem. But the steps will be exactly the same. Like you would find that p-value the exact same way. It's just that final step, you're comparing your p-value to a different alpha. Okay? So this kind of idea of alpha, this threshold we're setting, relates to, well, it actually is a type 1 error. Okay? So what are type 1 and type 2 errors? When we're trying to reject a null hypothesis, or if we reject or fail to reject, we can make mistakes, right? So if we incorrectly reject the null, so we reject the null when we shouldn't have, we call that a type 1 error. If we failed to reject the null, even though we should have, we'll call that a type 2 error. Okay? So, you could set this little table where if I reject the null when in fact it was true, I made the wrong decision, I made a type 1 error. If I failed to reject it when in fact I should have because it was false, that would be a type 2 error. And if I failed to reject when it was true, that was good. If I rejected when it wasn't true, that was also a correct decision. So we're really going to kind of focus on this type 1 error. So this type 1 error is essentially our alpha that we're setting. Okay? You can think about why that's the case. Why is alpha kind of the probability we make a type 1 error? Well, let's go back to this example, because I think it's a little bit easier. Notice, let's say the assumed true value here of 67, somehow after we do this hypothesis test, we end up getting the population data, and we figure out this was exactly the true value. So what we assumed to be true was in fact true. Well, then wherever we set alpha, so notice if I would have set kind of alpha, the area in the tail, to be 0.05, every time I saw a test statistic that corresponded to a value that was in this range, right? These were all sample mean values for which my test statistic would have led me to a p-value where I rejected, right? But if this in fact is the true mean, then I would have been making the wrong rejection decision for all these values, right? So when we set alpha, what we're really doing is saying, well, look, I know that if what I assume to be true is in fact the true mean, let's say it does end up being the true mean, that when I see sample mean values out here, they're all going to give me the probability I see something out here is always going to be less than that 0.05 that I set. it's not that, there's still very unlikely I'm going to see those as my sample mean values, but it is possible. And every time I do see one of those, if this in fact ends up being true, I'm going to be making the wrong rejection decision. I'm going to be making a type 1 error. But I'm okay with that because the probability of me seeing a sample mean value out here or any further, they're all going to be corresponding to p-values that are less than that alpha that I set, right? So I'll be wrong sometimes, right? If I set my alpha at 0.05, I'll be wrong 5% of the time if this in fact is the true mean. But even if this ends up being the true mean, I'll still be correct in my rejection decision 95% of the time. Right? But I'll be wrong, whatever that alpha level I set is. Okay? So alpha is our type 1 error, right? Or the probability that we make a rejection when we shouldn't have. Kind of a good, one way to think about this is like, let's say we go in and we assume that someone's not pregnant. Like that's kind of our null hypothesis. And we reject it, right? Even though in fact, clearly this person isn't pregnant, that's a type 1 error. When if we fail to reject it and we say, nope, the assumption that you're not pregnant is correct, we fail to reject it, even though very clearly that they are, right? The true state of nature is that they are, that'd be a type 2 error. So it's kind of an easy one to kind of think about. I'm not going to waste too much time on this. If we have, probably after the exam, we're going to still do some stuff with hypothesis testing. I'll revisit this idea of the type 2 error. It's kind of related to type 1 error. Actually, sorry, this is on the second slide. I'll kind of revisit this. It's related to the type 1 error, but I'll kind of hold off on that conversation until after the exam because I don't want to kind of complicate what we're doing or kind of provide any, require any more kind of knowledge about that for the upcoming exam. But type 1 error, we've really already been talking about it, right? Typically, it's just like confidence intervals. We set it at these lower values like 0.1, 0.05, 0.01, which correspond to our conventional 90, 95, and 99% confidence levels. So, so alpha is the probability we make a type 1 error. 1 minus alpha would be the probability that we don't, right? Or the probability of the time that will be correct. Okay. Any questions on this? We keep moving. Like I said, we'll revisit type 2 errors later. Oh, I always like this meme. So I made a type 1 error. I shouldn't have rejected you. So feel free to use that one. So we've got type 1 and type 2 errors. We've got about 10 minutes left. So I want to try to do one thing. So someone asked me in one of my sections to do some Excel work. I think I will do some of that on Wednesday to help give you a little bit better idea of how we would do this in Excel. That's not going to be required on the exam. It's not going to be required in anything leading up to the exam yet. But I want to show you a little bit just because some people, Excel kind of makes it easier for them to think about things. So the next thing we're going to talk about is combine two different principles. So first, where do I want to go? Here it is. We can do the exact same thing we were doing for means, population means, for population proportions, right? It's going to be a little bit different, right? But we have the same types of tests, right? Greater than or right tail test, less than or left tail test, or this not equal to or two-tailed test. Same principles apply. We're just looking at a different statistic here, the proportion instead of the mean. Right? So the steps are going to be exactly the same. It's just that when we turn proportions into z-values, remember the equation was a little bit different. So with our confidence intervals, we said, with our confidence intervals, when we wanted to find the standard deviation of my sample proportions, we said it should be equal to this, but we don't know what the population proportion was, so we had to use like our best estimate, which was to use the sample proportion. So this is what we did when we were looking at confidence intervals. Well, to calculate a test statistic, we think about the z statistic for a sample proportion. We're going to take, just like before, we took what? Our sample mean minus our sample proportion, our sample mean minus the assumed true mean. So take our sample proportion minus the assumed true proportion. And then what do we divide by? Well, here we had to divide by the standard deviation of our sample means. Now we're going to be dividing by the standard deviation of our sample proportions, right? We're dealing with a different statistic. Now, instead of using the standard deviation for our sample proportions that we were for confidence intervals, well, here we don't, we were estimating the population proportion here. Well, now we don't need to estimate it because we've assumed it's a certain value. So now our test statistic equation, when we're thinking about the standard deviation of our sample proportions down here, we use that assumed true population proportion to calculate that standard deviation for our sample proportions. So here we'll use that assumed true proportion. But once we have this test statistic equation, all the steps are exactly the same for hypothesis testing as they were when we were looking at population means and sample means. Okay. So that's the first thing, right, was we have a slightly different test statistic when we're dealing with proportions. Now, I mentioned last class, there's the p-value, but there's also the critical value approach. So I'm going to work through some sample proportion examples. We'll probably not get too far into today, but on Wednesday. And I'm going to use the critical value approach with those. However, I can use the p-value approach with proportions. I could use the critical value approach with means. It doesn't matter, right? I'm just going to use kind of proportion examples to show you the critical value approach. And I'll try to make the connection between the p-value and the critical value approach as well, because they're very similar, okay? So, what are we doing with critical values, okay? So critical values are going to be kind of threshold values that we set where we say, look, if I see a test statistic that's more extreme than the critical value I set, I know that I can reject the null hypothesis. Okay? So the critical value is going to be this value set such that if you see a test statistic that's more extreme or larger in absolute value than that test statistic, you know that you can reject the null. And if it's not, you know you fail to reject. Okay? So, this is going to be a little different for left or right or two-tailed tests, so I'll kind of go over that a little bit. But I want to try to make the connection between the p-value and the critical value approach as well. So, what were we doing before? I think the green one shows up a little better here. So we're going to be able to, we're dealing with sample proportions now. So what a critical value is going to be, and let's do a left-tailed test first. The critical value is going to be that z value that would correspond to a certain sample proportion that the probability of seeing something past this point is going to be whatever you set your type 1 errors at. So my critical value is going to be the z value that gives me my type 1 error in the tail, okay? So if I had an alpha of 0.05, how could I find that z value? Well, I'm going to work in an inverse, right, or in reverse. I know the area I want in the tail is 0.05. Actually, let's do an easier one because this one I can remember easily. So 0.025. If I look that area up in the middle of my standard normal table, I'll find that the z-score that gives me that area is negative 1.96. Now, for a left-tailed test, because we're using these small alpha values, we know our critical value should always be negative, right? Because, if I want anything less than 0.5, right, my critical value would have to be negative because 0.5 would be the area to the left of that mean of 0. So my critical value is the z value that corresponds to having alpha in that tail. So essentially, when I find that critical value, I can think about my rejection region is going to be if I find a test statistic anywhere in this range. So, let's say I see this as my sample proportion and I turn it into a test statistic. I know that that test statistic, if it falls in this range, I'm going to be able to reject the null hypothesis at. Well, why do I know that? Well, because if I look at that standard normal table, anytime I see a test statistic that's more extreme than negative 1.96, that just starts giving me an area in the tail that's smaller and smaller than 0.025, right? So I can set this threshold z value and say, if I see a test statistic that's any more extreme, right? Or here, kind of a larger negative value than negative 1.96, all those test statistics, let's say I had a test statistic right here, I know that the p-value associated with that test statistic is going to have to be smaller than alpha, right? So it's really just like comparing different sides of the coin here. When I was using the p-value approach, I was comparing the areas in the tail, alpha and my p-value. When I use the critical value approach, well, really what I'm doing there is I'm saying, is that test statistic in the rejection region? I'm saying, is that test statistic in absolute value, is it less than the absolute value of that critical value, right? I'm comparing the z-values instead of the areas in the tail that correspond to those z-values. So either way is okay. Another way to kind of think about these critical values is it's saying, well, look, I know that if I see anything that's more than 1.96 standard deviations below that assumed true value, then the probability of that occurring is going to be less than 0.025. Because if it was 1.96 standard deviations below, I know the probability of seeing something that's exactly 1.96 standard deviations below the mean is 0.025. So if I see something that's any further away, right, any larger number of standard deviations below, it's just going to be less and less likely I see something that far away, that, you know, more than negative 1.96 standard deviations away from that assumed true mean. So we're really just kind of comparing the area in the tail for the p-value approach, and then like the x-axis values, right, the z-values when we do our critical value approach. And when I write absolute value here, it's essentially ignoring the negative sign, because, you know, when we're dealing with negative values, being greater than is actually being a smaller negative value. So we take the absolute value to make it a little bit easier to kind of think about that. Okay. Any questions on that? Do one more thing before we get out of here, and we'll deal with a tougher one on Wednesday. So what if I was dealing with a right tail test? Well, everything's really going to work the exact same. I'm going to be thinking about, for a right tail test, only evidence on the right goes against the null. So I'm going to set the critical value that gives me alpha in the right tail, right? Let's say we do alpha of 0.025. What's the area going to be in the what's the critical value going to be that would give us 0.025 in the upper right tail? Well, it's going to be the exact same value as the critical value for a left tail test, but we're dealing with the right side of the distribution, so positive 1.96. Right? So our left and our right tailed critical values will be exactly the same. It's just for a right tail test, they're going to be positive. For a left tailed test, they're going to be negative. But then it's the same approach. You know, if I see a test statistic here, we can think about anything more extreme than my critical value is now to the right. So if I see a test statistic in this region that's in the rejection region, I can reject. If it's not in the rejection region, like it's somewhere out here, well, now I fail to reject. And once again, this test statistic, the area to the right of that would be the p-value. Right? So any test statistic I see past this point is going to be giving me an area smaller than 0.025. And if I only reject when the p-value is less than alpha, I'll reject. So any test statistic that's larger than my critical value, I can reject. And here, you know, now when I take the absolute value, it doesn't change anything because they were already positive. But here it's that, okay, if my test statistic, right, is greater than, actually, sorry, I think I had this backwards here, didn't I? If my test statistic is greater than my critical value, I reject. If my test statistic is greater than my critical value, I reject, right? Or more extreme than my critical value. Okay. Any questions on that? I went a little bit over here, so I got to let you guys out. But I'll probably put up, I'm going to put up an online quiz when I get back to my office this afternoon. There'll probably be a problem that gets you kind of an example that you can start to work through one of these on your own. And then maybe just a couple general questions, more so for me to get an idea about where everyone's understanding is at and kind of how to proceed for Wednesday and Friday. Okay? All right. I will see you guys on Wednesday.